Okay, before I forget this again. So maybe we do the open problems. There's just one problem from the last session, question 5, to give a subnearing which is not a left or a right ideal, or a right ideal which is not a left ideal, and conversely. For this, perhaps it's a good idea to investigate two subnearings which we have mentioned over and over again. These are n sub naught and n sub c, the constant part. And the constant part is easily seen to be a subgroup, and it yeah, but it's not necessarily a normal subgroup, so it doesn't qualify as a left or right ideal. For instance, take x, no, take x and y in n such that n x plus y is not the same as y plus x. So we need, of course, a non-abelian group. And then we look at the constant, which always has a value c, a value x. C composed with anything is this value x. And then we look at this, the identity plus c minus the identity. And if we take this at the place 0, we get identity of 0 plus c of 0, which is c, minus the identity of 0. So we get, no, that was wrong. Excuse me. No, c of x is always x. So we get this here. While on the other, so we see that this here is not constant. And that means that the constant elements do form a subgroup, but it's not. It's neither. It's not a normal subgroup, and so it's nothing than a subgroup. Well, it's a subnearing that's easily seen, but that's about it. What about n sub naught? This can easily be seen to be a normal subgroup, always. And why is this the case? Well, if we have, say n sub naught in n sub naught, and if we have some m in n, then m plus n sub naught minus m, that has to be back in n sub naught. And if we apply 0 on the right-hand side, we see this is m composed with 0 plus n composed with 0, which is 0, minus m composed with 0. And no matter what this is, this difference is 0. And so you see that this is a normal subgroup, and it's also easy to see that it's a left ideal. For a left ideal, take again n sub naught in n sub naught, take again some n and m in n, and now we have this strange looking condition for left ideals, that we have n plus n sub naught minus N, that's sufficient. We don't need an M. Oh, yes, here we need it. Composed with M. This has to be back in N sub naught. How do we check it? We simply apply 0 to this, so we get N plus N naught minus N composed with M composed with 0. And here you see the same happens as above. We get N M0, here 0, and here minus NM0, and so we get 0 again. And this means that we are back in N sub naught. And this means that N sub naught is in fact a left ideal, but usually it's not a right ideal. For that, take some N sub naught in N sub naught, take some M from outside, and we have to find out if we are back to N sub naught. A good idea is to take a constant C in N sub C, such that C is not the same as 0. Of course, if we do not have any constants, then N sub naught is the whole of M, and it's an ideal in this case. But N of naught composed with C, if we apply this to 0, we get N sub naught composed with C. And N sub naught composed with C is then certainly not right idea, yes. And this is certainly not 0 all the time. We just take some N sub naught, which is not 0 on C. Now, what about having a right ideal, which is not a left ideal? That's very easy. Take the constants again in the case that we have an abelian group, n plus, and then it's automatically normal, and it's a right ideal, but it's not a left ideal as before. Has anybody else some good things, some good examples of left ideals which are not right ideals, and conversely, other than that? Well, if not, then we can perhaps simply start the usual lecture. But since the corona cases are increasing and increasing, maybe I should do some precaution for you. Maybe I'll work in this way in order to prevent the virus to come to you via the internet. That can be here. I don't know. And it's very easy to do that. It's very hard to understand me. So maybe not. Uh, yeah. As I said, the topic will be near fields. It's already in here. And if we look at near fields, what's the definition? Of course, the definition is that the non-zero elements should also form a group in a near-ring. So this is a good way and to tell this. And what would be the smallest near field on Earth? Well, we had last time the smallest near-ring on Earth, which is the constant nearing on two elements. And so let's do the operation table again. The addition is just modular 2, and the multiplication is the constant one. Now you see this structure does not have an identity. You can see it from the operation table here. And so it's, but on the other hand, if you take the non-zero elements, then it's very easy. The non-zero elements are just, it's just one, and this forms a group. And so we have a very awkward situation that we have a nearing, which is constant as well, and yet should qualify as a near field, but it doesn't even have an identity. And so this is a very strange situation. And due to that, many people uh, blackmail this example, the baby, and we maybe we do the same, that we do not allow the a near field to be of this type. So we simply, by law or by verdict, we simply uh, say this is not a near field. By definition or by exclusion. We simply don't like a near field to have such a strange structure. And maybe uh, you have seen now the operation table. Maybe you don't know the whole thing about operation tables. I tried last time, so maybe I'll try again to show it to you. Uh, Maybe it works now. Uh, so maybe you can see it. That's an operation table, and uh, and the second part of this is also nice, and it has disappeared again. Shit, I don't know how to do this. Uh, in any case, uh, but operation tables, you can see a lot of things, and we will see more of this as time goes on. The first thing is a little remark. Every near field which has not two elements like this here is zero-symmetric. Excuse me, every near field, I will abbreviate it by NF, uh, is with greater than equal to two elements is zero-symmetric. That's easy. Simply take an element x, which is not zero and not one, since we have at least, no, excuse me, greater than two, of course. Since we have at least three elements, we must have an x like that. And if you take then x, I have to do it. No, I'm sorry. Uh, Suppose C in this near field is constant, then we have C composed with zero. Is C composed with any other element x, as we have seen, which means that since we are in a near field, we can cancel if C is a constant unequal to zero. And so we would have 0 is equal to x for all x. And this means that the near field only has two elements. Now, basically, near fields have been the first object of a study in the whole area of near rings and near fields. And it was back to 1905 when L.E. Dixon wondered if the axioms for a skew field, which is a non-commutative field, if they are independent or not. So maybe uh, he thought maybe the uh, one distributive law will imply the other one, and if you don't have any commutativity, then it might be and so he constructed the first proper near field in such a way that he took a finite field and screwed the multiplication in a brutal way. And this is something we will need later on anyhow. So let's define this. So that's the first time we have a proper near field on our Earth. And we start with a field F. And for this field, we define a so-called coupling map. Uh, in such a, let's call it capital Phi, which goes from the field to the automorphisms of F plus dot. Oh, let's make a dot here. In such a way that every element F will be mapped to some, let's say, Phi sub F, an automorphism of F, and we need a certain condition. Why this crazy condition comes into play will be clear a little later. And we first start with this property. It's called the coupling property phi f, composed with this phi g. That should be the same as phi sub phi, phi sub phi of f sub f of g times f here. So this is a rather strange condition, and you might wonder why it's necessary. But the good thing is, if you have a coupling map like that, then you get a near field out of this. Then you define a new multiplication, a composition, uh, let's say sub phi, because it depends on this coupling map in such a way that two elements are, let's say, f and g again, multiplied in such a way that we take phi sub g of f times the old times the old g. So this is a rather strange way to do this, but if you check all the uh, details, then you'll find out that in this way our near field F with the same addition as before, but with the new addition composition coming from phi is a near field. And since Dixon was the first one who used this or who found this construction, these type of near fields are named after him, and they are called Dixon near fields. So you can do it with any field. We can start with any field and squeeze the multiplication in this way. One example, a trivial example for phi would be the following. Let's take the phi to be that this all small phi f's are the identity map. Then you see you get simply the old multiplication back, and so you get a field. But in general, you do not get a field; you get a proper near field out of this. Sometimes we use this way that we denote this as f phi up there to say this is the derived near field from f, and we will see that this is a very useful construction. Now you get a certain class of near fields, the Dixon near fields, and you might ask if there are others around. But before that, we would like to look at an example of the smallest real near field, so to speak, except the two element example we had before. And for that, it turns out that we have to go to order 9. We start with the field in our example. The field F would be the Galois field of order 9. And we have to find a good way to do this. So I don't want to make all these computations. I'll try again to get the operation table here. And B. No. Oh, here it is. Can you see this on your screen? That
I can see something about Zoom meetings which needs to be opened.
Oh. I'm sorry. I did some training before, but can you see it now?
Yes.
Okay, it's in my picture. So can you see the operation table of the 9-element field?
Mhm.
Okay, fine. So as you know, the Galois field with 9 elements can be constructed in a way that we take the polynomials over the 3-element field, sets up 3, and factor out an irreducible polynomial. In this case, we do it with x squared plus 1. And then you get all elements or different elements in such a way that you simply take all polynomials of degree 0 or 1 uh, with coefficients from set sub 3. The addition there is as usual, and the multiplication, as you know, is so that we simply take the usual multiplication in the field uh, or with polynomials, and then we divide it by x squared plus 1 and take the remainder. So the new multiplication, uh, that's the old multiplication, and the new multiplication, you can get it in this way, that you take these elements here and we'll find out what the coupling map will look like. But first of all, this gives uh, the smallest proper Dixon near field, and also you see that I have grouped it in a different way, not 0, 1, or 1 plus x, 0, 1, 2, x. They form a subgroup, as you see, and the multiplication table turns out to be this way. Uh, we have a unit element, as you see from this multiplication table, which is the number 1. It's a two-sided unit, and it's just the old unit element. And in fact, when you are doing this construction, the old unit in the field will still be the same unit in the near field. The non-zero elements, if you take away the first row and first column here in this multiplication table, uh, these non-zero elements do form a group, and it turns out that it's a non-abelian group, of course, to make it into a non-field, and it's the quaternion group of order 8. And the coupling map looks the following way. It maps these elements, which I mentioned first, grouped first here, 0, 1, 2, x and 2x, into the identity, and the other elements are mapped to the map phi, which takes every element to its third power. That simply turns out from this construction here, and it's a good example for a non-trivial uh, Dixon map or a derivation map or coupling map. And so we see that we can really construct use non-trivial examples for that. Now, after that, we might take, how do I get this? Okay, so we are back to the usual situation now. We collect some facts about near fields. Quite a number of these facts are not quite easy to prove. In fact, some proofs are really long. I'll tell more about this in a moment. But before I erase this, what's the reason for this strange condition? The reason is very, very simple. It's simply uh, the condition which makes this new operation to be associative. If you simply translate the associativity condition into the coupling map, you get exactly this equation here. And so that's the reason why we need it. What we would need without this would be a multiplicatively non-associative near field, and I'll come back to these structures uh, later today. So let's collect some facts about near fields. And the first one will be theorem one. Uh, and there are many authors. I just mentioned two. One that's von Neumann. Uh, he's the not John von Neumann, the famous one who invented basically uh, computers and everything else. It's his son, uh, Bernhard Neumann, who also became very, very prominent in group theory and in algebra altogether. And second one, Helmut Karzel. Uh, he lives in Hamburg, and both of them have uh, gotten the same result with a slightly different meanings, namely that a near field, whenever I write n in this context, it will be a near field, then n plus is abelian. So the addition is automatically abelian, which is non-trivial, and it needs a little effort to prove this. It's also quite interesting because it answers a question of Dixon in some other way, namely, if you take all the axioms of a near field, then the uh, remaining axiom that the addition is uh, commutative is a consequence of the other axioms. So it was quite surprising to get this uh, result. The next thing is we take as a definition n sub d. This is the set of all d in n such that d composed with n plus m is d composed with n plus d composed with m for all n and m. So that's basically the, uh, as you might call it, the set of distributive elements in the near field. This is quite important. And question 6 is appropriate now, is show that n sub d is a skew field. That's not very hard to prove that it's a skew field. And we see that in the finite case, since every finite skew field is a field, it means that n sub d is automatically uh, a, would be a subfield of n. And in fact, it turns out that this is also true in the general case. Uh, so fact would be that n sub d is always a commutative field, not only in the finite case, but also in the infinite one. Now, from this, it means that within our near field, we do have a smaller near field, which actually is a field, and it's quite trivial and a matter of simple computations to find out that n is then or can be considered as a vector space over n sub d. So n is a vector space over the subfield of distributive elements. That means if the uh, as a vector space over this field n sub d, if the dimension is finite, then we see that n must be a power of n sub d in the group theoretic sense. And this means that so if n is finite, then the size of n must be some p to the n for p prime. And moreover, the additive group of n is elementary abelian. It's a direct sum of Cp times Cp times Cp and so on, as often as the dimension uh, of n is. And so we see we do not have to look for a finite near field of order, say, 10 or so. All finite near fields must have a prime power order. And in fact, our example, which we had before of order 9, 9 is a very good prime power. So we know already quite a bit about the addition in a near field. It's abelian, in fact, elementary abelian. And we need more about the structure of a near field, of a finite near field itself. And that seems to be very tough. For instance, yeah, even if you say you confine your attention to finite near fields, uh, you know that the characterization of finite fields is rather easy, but the characterization of finite near fields was much, much harder. And in fact, there is a very famous theorem uh, that's theorem 2, due to Sassenhaus. Uh, and it dates back to 1936. So, so it's quite an old theorem. Uh, it was basically one of the first papers of Hans Sassenhaus, and he had a monumental paper showing or characterizing all finite near fields. And his statement was all finite near fields are Dixon near fields. Uh, with some exceptions, namely 7 exceptions, with of order. The first one, the smallest one, would be order 5 squared. Then we have 7 squared, 11 squared, and I write 11 squared again, because for order 11 squared, there do exist 2 non-Dixon near fields, which are non-isomorphic, which is also quite interesting. And then we have 23 squared, 29 squared and 59 squared. So you see that all of them are of order p squared for some primes up to 59. And these exceptional near fields, these can be described also very well. And Sassenhaus described it in such a way that, for instance, for 5 squared, uh, well, 5 squared would be then derived from a finite field of order 5 squared. So a two-dimensional field over the uh, 5-element field, and the two element that these excuse me these elements here can be written as matrices, and this one can say the uh, near field is generated by the 0 minus 1 and 1 0, and the matrix 1 minus 2 minus 1 minus 2. And similar for the other cases, sometimes you need 3 generators. This is also always one of the generators. And so also the exceptional near fields are really well understood. And the Dixonian near fields, the Dixon near fields, they are also studied in detail. And this is a very uh, satisfactory result to say that all finite near fields are now completely characterized. And that was in a pretty old paper. The proof is very, very long and not really very transparent. And few people have succeeded in reading this proof. And so there were some efforts done to simplify the proof to make it more easily understandable. And I've just heard a few weeks ago that two Germans succeeded in this task. They found a more transparent proof of only, I think, 20 pages now of this result. And so this they say it's just under publication. And so when it's out, we will have a much better understanding of finite near fields, I think. So the question remains, what happens with the infinite near fields? Do they exist, infinite near fields? Yes, they do. You start with an infinite field, use a coupling map, and if it's not a trivial coupling map, you arrive at a near field, a proper near field, an infinite near field. Maybe it's a good idea to introduce also the concept of the characteristic. It's defined in the same way as for fields. Characteristic is the smallest integer n, such that n times every element is 0, and n always turns out to be a prime, same proof as for fields. And so all near fields can have characteristic as a prime p, or they can have characteristic 0. Now it was open for a long time what happened to the infinite case. And there is another theorem 3, also by Sassenhaus. And this is much, much later, 1987. So you see, it was more than 50 years after the first publication that Sassenhaus came out with another big paper saying that uh, there exist infinite non-Dixon near fields of every prime characteristic. So that was pretty surprising. They are infinite, but they have a finite characteristic, which has to be a prime. And for every prime, you find a non-Dixon near field with this property. In fact, this was one of the first papers of Sassenhaus here. Then he did a lot in group theory and other areas. And this theorem 3 here was one of the last papers of Sassenhaus. So at the end of his life, he came back to near fields and solved this problem as well. By the way, Sassenhaus was a honorary professor at our university in Linz. And when he lived there, he always lived up on the hill overlooking Linz, the so-called Böstlingberg. And he always lived in the same house. And this house was then quickly renamed as Sassenhaus House. And he was full of energy. I remember when he first came to Linz, uh, I, together with a colleague, we picked him up from the train station. It was a very hot summer day, and he had about 10 hours ride from northern Germany to Austria. It, and he was pretty old at that time already. So we thought we'll bring him to the accommodation as soon as possible. But he protested and said, no, no, he wants to see the nightlife of Linz first. And it was about 2 or 2:30 in the morning that we got him to bed. Uh, and then at 6 o'clock next morning, he showed up at the institute and was wondering why nobody was there. So he was so full of energy, and this is reflected by the big number of papers, of important papers he has written. So now we might start to look, after the characterization of near fields, to look at the question, what are near fields perhaps good for? And there are quite a number of areas where near fields, and I mean here proper near fields, do play a prominent role. Uh, it's still not dry enough. It's this board was very cheap, but it's hard to clean, and I hope the uh, chalk dust will not be uh, make the whole thing invisible. But at least the chalk dust only affects really me because it's a very good sample of microdust. So let's take the first application to geometry. Excuse me. Suppose you talk about the usual affine plane over the real numbers, and whenever you start to talk about the plane, there's one immediate reaction by all people who talk about it. The first thing is that they start to do this. Uh, what's the reason? Because uh, in here you can name the points or characterize the points by pairs, and you can characterize the lines by equations. And so it's such a immediate reaction to draw something like that that one might wonder what happens with other planes than just the usual affine plane uh, uh, R squared, or in more general F squared, where F is a field, uh, because you can take any field, F, finite or infinite, and characterize the points as pairs and characterize the lines, at least yeah, the lines by linear equations. But what happens with other types of geometries? Sometimes you find all, if you look at geometry, you find all kinds of definitions of planes, Disarchean planes, non-Disarchean planes, and so on and so on. And sometimes it's only uh, it's very hard to work in these areas because sometimes you cannot have coordinates like in here, but you have to describe the line which goes from point P1 to the point P2, and it becomes very cumbersome after a while. So many people were looking for a way to get also coordinates to other types of planes which are studied in geometry. In fact, it was perhaps the most big advantage for geometry in the past centuries that uh, coordinates were invented, because then it was much easier to describe all kinds of phenomena of geometric properties by a very elegant method. So, what's needed to have coordinates? What's needed is some uh, maybe some uh, set here. Let's call this set to be S, here also S, in such a way that the points are simply uh, the elements of S cross S. Okay, that can be done with every set S, but you would like to have the lines to be characterized in the usual way, say y is equal to, and I don't write a times x now, but I write x times a for a certain reason plus b, at least the non-vertical lines. And you might say, okay, in this case, it's not sufficient to have S a set. You must have an addition for uh, S, and since you have a multiplication here, so you have to have a structure which has at least some kind of addition, some kind of multiplication. Well, this can be all kind of structures which have this. You don't need any other law just in order to describe it, this. But in order to get a decent type of geometry, you would like to have some, or you need some special rules like in here. So you quickly will find that you need to have S plus to be a group, maybe not necessarily a billion, but at least a group, and that the multiplication should be associative. In some case, it's not, but in order to uh, get some good things, you need a little more than just a group with a multiplication which has nothing to do with the addition. So one property which always comes to our mind when we are looking at lines is this, that two non-parallel lines should have a unique point of intersection. So if you have one line, y is equal to xa plus b, and another line, y is equal to xc plus d, and if they are not parallel, which means that a is not the same as c, then you would like to have a unique point of intersection. What happens to make things short, to assume that S plus dot happens to be a near field. This turns out to be especially successful in getting interesting types of geometric planes here. What can we do in the case of nearings? So suppose that S is a near field. Well, we can subtract these two things and to get a unique point of intersection, and you'll get 0 here. Or this way, that was say that x sub a plus b should be the same as x sub c plus d. Now we can put the x sub c on the other side, so we have x sub a minus x sub c is equal to d minus b. Provided we have commutativity, but if we start with a near field, we always have a commutative addition. And now we sorry. Sorry, I sometimes get into conflict between left and right distributive. So let's write the lines. I was thinking it's ax plus b. Sorry about that. And here you see what I have.
Excuse me. Just a question. I cannot read the last line, probably because I don't have very good connection. So if you can read it.
I'll better write it. So you have, if you have this, you can write a times x minus c times x is equal to d minus b. Ax minus cx is d minus b. And
Okay, thank you.
You have the correct distributive law. I tend to write this as a minus c times x is d minus b. And since a minus c is not the same as 0, you see if you are in a near field, you have x, you can determine it uniquely, and you have a unique solution for x, and then you have a unique solution for y. So this will lead to a unique solution. And that means if we are in a near field, we have the nice property that two non-parallel lines always have a unique point of intersection. And this is something which is where you get a lot of applause if you work in groups in geometry. And then it turns out that for special properties of the geometric plane, you get special properties of the corresponding near field S, and we call it the S, the coordinatizing near field for this plane. And conversely, so what you can build up is some sort of a dictionary between geometry and algebra in such a way that properties of geometric planes will be reflected in properties of the near field. Now this means that we have a nice way to deal with geometry, because then a lot of planes which have been to be described in a cumbersome way before can now be coordinatized by near field, and so it's much easier to do the work there. Like it's much easier in the usual plain ask word to work with coordinates instead of working in such a way to say, let's take the line from here to there and the other line from there here to another point and so on. Now, this property here is a property which uh, will come up later again. And we also will like to find out what happens if we have the other way around, XA instead of AX. And that's a condition of so-called planarity, and we'll come back to this later on. Now it's a good perhaps time to ask question 7. Show that all maps of the form X goes into, how does this, XA now plus B, where X, A, B are in the near field N, that all these maps, and where A is unequal to 0, have no fixed point. So there's no X which is mapped into X. All elements X are mapped to some other elements. And this is this property of being fixed point free will appear later on, and in another context again, and it's quite an interesting thing to say that this is an example of a fixed point free map. Well, not quite true. We must say except if A is equal to unless A is unequal to 1. Because if A is equal to 1, it means X goes into X plus B. And so if B is equal to 0, all elements X would be fixed points. Otherwise, if B is unequal to 0, we still have no fixed point. So two extremes can happen, no fixed point at all, or only fixed points. Then we just have the identity map. Now that's not all what near fields have to offer as applications. We might take application 2. Application 2 goes to group theory. So, nearings and near fields get a lot benefit from group theory, and it's also possible to give group theory something back in exchange. And this concerns, in fact, in essential transformation groups. What is the setup for that? We have a group which is a subgroup of the symmetric group on X for a set X. This is just the set of all F from X to X, such that F is bijective. Sometimes bijective self-maps are also called permutations, and this means that we have a group of permutations on some set X, and we say that G acts on X.
Mhm.
By taking every element, any element X, to some G of X. And now you can have a certain situation, namely that G will take X to any other destination. In this case, G is said to be transitive on X if from any X you can reach any other Y in this set X. This is nice if it happens and can be wrong as well. Usually what you get is an interesting structure of having some sort of so-called orbits where the elements are moved around. And then it's also often interesting to look at another case, namely that she doesn't bring any x to some g of x or some y, but maybe in a unique way, so that there's just one g taking x to y. Uh, that means if x and y are two members of capital X, then there is exactly one bus which brings x to y, and not two or three or more different buses. And that can also be done in this way, that we look at, say, pairs x1, x2, and ask if x1, x2 can be brought into, uh, say, y1, y2, then we call it doubly transitive. And if it's possible by just exactly one G, it's called sharply two transitive. And maybe we give the definition in such a way that G acts k-fold, sharply k-fold transitive on X if the following happens: if all x1 up to x sub k, such that xi is different from each xj, and for all y1 up to yk, there exists exactly one g in G which maps these x's in the corresponding y, so that G of xi is the same as y sub I for all I. Of course, you have to have the elements here to be pairwise different, because otherwise you cannot prescribe the values y1, yk, and so on. And so it's quite interesting to find out about these sharply k-fold transitive groups. Now, quite a bit was known about this k-fold transitive groups already, namely, may I erase this here, in such a way, what if k is equal to 1, then G is simply called a regular permutation group on X, and regular permutation groups are really well understood. So there's a good theory about that, and one knows what one has to expect in a regular permutation group. Some very nice properties are around there. Then the other case is k equal to 2, k equal to 3, and then I can abbreviate the whole thing by saying k bigger or equal to 4. And surprisingly, in this way, in this case, it's known already what happens. It's known since the last centuries, last century, by a certain Camille Jordan, and he found out that very few groups qualify to this, namely the group G must be either there's n, where n is greater or equal to 4, I believe, or 6, 4, yeah. The full symmetric group on n elements, or equal to a sub n, the alternating group, where n is bigger or equal to 6, or else two exceptions, M11 or M sub 12. These are the so-called Mathieu groups, number 11 and 12. They are quite large groups already, and their size is somewhere in the area of 10 to the 17 or so. That means that one has one knows exactly what happens with k equal to 4, or all other cases later on. Now, that means that just two cases here were open, k equal to 2 and k equal to 3. And now it was a good question to find that out, and maybe we'll make an example for k equal to 2, just to get an example of a sharply two transitive group. There. So if n is k is equal to 2, suppose we take a field, maybe the field of real numbers, and take R to be the set X. And what do we have for sharply two transitive groups? We have that for all x1 and x2, which are different, and for all y1, y2, we find a map from this transitive group, which maps x1 into y1 and x2 into y2. Now, what can we take as a group? One group which acts on the set of real numbers now is the group G of all maps x going into ax plus b, where a is not 0. All these maps are then bijective. And what does it mean? to get this property to find a map. Let's call it F here, which maps x1 into y1 and x2 into y2. Well, simply look at the picture. Now I again draw this thing. Suppose here we have x1 and here x2, and here maybe y1 and here y2. Is it possible to find a permutation which takes this point into this point of this form? And you know that's very easy. You simply take the line connecting these points, and this line should have the equation y is equal to ax plus b. And you know, if these 2 points are different, which is guaranteed by x1 unequal to x2, well, then there exists always a unique line, which means there exists a unique map F, which takes x1 into y1 and x2 into y2. So this is a very nice example of a sharply two transitive permutation group on the set of real numbers, and you see that you can exchange the real numbers by any other field, maybe also by near field. And before we go to this, we should mention there's another concept which is related to sharply twofold transitivity or to twofold transitivity. Uh, this is sometimes called 1.5-fold transitivity, which means that for x1, x2, y1, y2, we always find a map which takes x1 into y1 and x2 into y2, or take x1 into y2 and x2 into y1. So it takes the two-element set into the two-element set, but we don't know if we will reach y1 or y2 first. I learned this 1.5 transitive permutation groups from, as usual, from Gerhard Betsch, and he showed that these can be used to get interesting combinatorial structures, which we'll mention later on, and this leads to very good designs of experiments later on, designs for statistical experiments. So now we find out what happens if we take, instead of a field R or in the other field, what happens if we take a near field? And we have the question is same as up here, true for near fields instead of the field R. Well, in near fields, you also can build up the same group of permutations, and the question is, does it hold? Will it give a twofold transitive permutation group? And the theorem is yes. It will also be sharply two transitive, and the thing which is very, very interesting is the converse. Suppose, or will you get all sharply transitive permutation groups in such a way? So the next thing is, yes, one gets all. very surprising. So in every case, you have a sharply two transitive permutation group. You can find in near field acting by group like this, and this which really gives the same situation in a certain sense, like the two transitive, sharply two transitive permutation group you started with. So again, this was a very, very uh, uh, nice to that all sharply two transitive permutation groups uh, were found. Yeah, with some exception uh, in the finite case. The next thing is, what about the infinite case? Yeah, you get still sharply two transitive permutation groups, but you need another structure which is a little more general than near fields. What you need are so-called near domains, and these are can be loosely described as multiplicatively non-associative near fields. And since then, since that was discovered, the uh, a whole group of mathematicians was looking to find out if there do exist near domains. And as far as I know, the search is still going on. One, they must be infinite, but nobody has ever seen an example, and nobody has shown that near fields do not, near domains are precisely near fields.
Mhm.
It's still an open problem. Yeah, in here there was another case which was open. That was the case of k equal to 3. These are uh, sharply three transitive permutation groups. And again, you get something uh, which you uh, which sounds similar to this. Uh, all sharply three transitive permutation groups are can be described as maps of the type X goes into uh, a x plus b divided by cx plus d, where the determinant a times d is not the same as c times b, uh, and where the whole thing happens over something like a near field, and let's call it uh, a generalized near field. So the description of these generalizations is not easy, and but it's also very satisfactory that one has this. Some people call it Möbius transforms as the example of sharply three transitive permutation groups. And that since the next step would be n equal to 4 and so on, uh, this case was settled already. So with this help, basically with the help of near fields, one now has a complete description of all sharply transitive permutation groups, at least in the finite case. And this is very nice because uh, without near fields, uh, it seemed to be completely hopeless to characterize all these sharply k-fold transitive permutation groups. Maybe a short warning if you speak about near fields, uh, then you sometimes will hear nowadays near fields in another context, and it was Bernhard Neumann, which I mentioned before, who once sent me a paper about near fields, and it turned out to be what's called now uh, near fields communications. So if you have a credit card and if you show it close to a machine, then it will deduct money from your account. This near field communication is interesting because it has the name near field in it, but it concerns a completely different area, of course. Now, finally, let me mention another thing which might be interesting. What happens if we take this uh, coupling maps, which we started with, and apply it not to fields but to a ring? Then we get a derived ring from that, and it's called a Dixon nearing. And also, Dixon nearings were studied very early, for instance, by Carl Maxson already in the year 1970. There was a longer paper on this Dixon nearings. They have similar but properties, but of course, it's not as nice. Things don't go as nicely as in the case of near fields, which is understandable. But it's possible to study this concept in a much more general sense. And so this construction altogether is a real success story. Now, let's stop for today, but I would like to ask you, especially to the students among you, if it might be interesting for you or helpful for you at the end of the course to get a certificate that you have participated. On the other hand, people in the personal department usually know that somebody has participated in a course. It can mean very little. And so I offer also to those of you who are interested in that to make a small exam at the end. And in this case, you will get a certificate that you have participated and took an examination successfully, and that maybe might be of help for you in some other areas. Uh, I say this because it helped me when I was a student. I took a course uh, in the University of Vienna. Uh, the speaker was the famous lady uh, Olga Tauski-Todd, who was very prominent in the theory of matrices and has a big name now. And I took a course there, got a great report, and with this, that helped me basically to uh, come in to enter any seminar I liked, I found interesting at the University of Vienna as a student. And so think about that, and I'll ask you perhaps later again if you are interested in that. So thanks again for being here in this course again, and I wish you a good time. As I mentioned in one of my emails, next week we'll have a national holiday in Austria, and in 2 weeks we will celebrate the All Saints' Day. So these days will be, by definition, free, and
All Souls
all
Day.
souls, yes, all souls. All the day before is all saints. Yes, thank you. And so we'll have no lecture in the next 2 weeks, and then
Mhm.
we'll see us again in 3 weeks. Hope you stay healthy. Hope you still come back after 3 weeks to this lecture. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you, and goodbye.
Goodbye.
Goodbye. And thanks.
Okay, so thanks and see you later.
Thank you.